Oh, sorry about that. Let's get rid of this music here. Alright, so everything seems to be working now. I did test the mouse, or not the mouse, but the stylus. It seems to be working now. Woo, I can drag all over the place. Okay, cool. If you're just watching the video, the previous video got trashed because my pen didn't work. So it works now. I can draw all over the place. So hooray, it works. So just a repeat of the announcements from before. Today we're going to do Unit 13 and also talk about lab worksheet number 4. Quiz number 6 is due tonight. It closes. Make sure you get that in by the deadline, or you won't be able to do it. Quiz number 7 and this lab worksheet we're going to talk about will be due next Tuesday on the 1st. So let's get started here and talk about empirical formulas. So the gist of empirical formulas is that you get the identity of the molecule in terms of the ratio of what elements are there, but you may not actually get the actual correct formula, as we're going to see in a second here. So an empirical formula is the simplest ratio of its elements. So some examples of that would be like if I had something with twice as many fluorine atoms in it than nitrogen, NF2 could be its empirical formula. Now, N2F4 right here, this is not an empirical formula because you can divide a common number out, that common number being 2. However, N2F4 does exist. So how would I tell the difference between NF2 and N2F4? We had to do other things to calculate this later. The whole point of the empirical formula is to just give you the simplest ratio between all of the elements that are present. So I've got a bunch here. And what we want to do to determine if they are empirical formulas is there a number we can divide out? If the answer is no, it's an empirical formula. So CO2, there's no number we can divide out. So this is an empirical formula. 1 is not a number we divide out because 1 doesn't do anything to the formula. However, 2 is. I could divide this by 2, and I would get the empirical formula HO. In other words, I could not distinguish a sample of this from this if I was only looking at its empirical formula, because both of them have the same amount of H and O in there. Down here, there's no number I could divide out. If I divide by 2, then I get a fraction. I can't have fractional atoms. You can't have half an atom. So this one is actually an empirical formula, even though there are no 1s in there. You don't necessarily have to have a 1 present. As long as there is no whole number, you can divide out and still get whole numbers. The bottom one, however, I can divide a number out. We can divide that one by 2 as well. And I'd get HCO2. Now, it's important to note that empirical formulas do not represent necessarily substances that exist. They just represent the ratio. And here is why this could be helpful, but also problematic. So if we go over here, and I do an analysis of a compound that has just carbon, and I need to get the right color for oxygen here, and oxygen in it. And I don't know what the coefficients are. I'm just going to label them like this. Let's suppose that I do an analysis of this. And I find out that the amount of carbon in my sample is this much. Boop, 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 boop. I have to actually hit the tablet there. Okay, so I have that much carbon. And then I do the same thing for oxygen, and I notice that this is the result that I get. You could look at those and go, oh, the ratio of these is the same. Oops, I gotta get my pen back to what it was. There we go. And so you might think, okay, well, my compound must therefore be carbon monoxide. However, I have no idea about the number of molecules that I split apart because molecules are really, 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 really small, and we don't have tweezers that we can get an individual molecule, pull it apart like it was made of Legos or a model or something, and just look at that. We're looking at giant samples here with trillions upon trillions upon trillions of atoms in them. So as a result, if I had put CO in the detector, I would get the results that you see up here. But if I put this in the detector, I would also see that. And if I put this in the detector, I would still see the same thing. What I would know is that I could have any molecule with this formula, right? Where X is the same number for both. And what I also know is that I don't have this. This is not correct because this would be twice as much oxygen as carbon. Nor can I have this because that would be twice as much carbon as oxygen. So I can eliminate a lot of possibilities here, but really all I can do is narrow it down. Now the good news is that for ionic compounds, this works out great for us because ionic compounds are empirical formulas. And an ionic compound is just a giant lattice, and the formula that we write out for it is the simplest ratio of the elements. So if we're doing an analysis of an ionic compound, of which the substance in our lab that we're going to be doing this week is an ionic compound, you get the empirical formula and you're done. You're all set. But if you're working with something molecular, you may or may not get the substance that you're looking for. And we have an extra step that we'll tack on the end that deals with that. So that's the logic behind empirical formulas, is that we get a ratio of the elements. For ionic compounds, that's excellent. For substances that are not ionic, not so great. We have to do something more to it. So that's where this term comes in. The molecular formula of a compound is its actual formula. Now, it's molecular because this only applies to molecules and stuff too, right? How do we figure out the molecular formula of a compound? To get from the empirical formula to the molecular formula, we multiply by some number. And so the relationship is just simply look at both of them. What is the number that I use to multiply these two things to get, or to multiply this first thing to get the second one? And you should be looking at that and going, oh, well, obviously they all increase by a factor of 6. So the multiplier here would be 6. Now, how you determine the multiplier, we'll talk about later on today. For these first few examples, we're just going to try and figure out the empirical formulas of stuff, because that's going to be relevant to the lab. Then we're going to talk about the lab, where you'll have to calculate an empirical formula. And then we'll talk about molecular formulas at the very end. So let's jump right into an example here. If I give you a substance, and I know its elemental composition, so I give you its mass percentage, then you can figure out its empirical formula in 3 steps. The first step usually is just given to you in some capacity. Figure out how much of each element you have in grams. I will either give you a mass percentage, or I will give you, oh, I break down this element and I have this many of this element and this many of this element. Once you know the number of grams that you have, the next step is to just turn them into moles. That's trivial. We did that in Unit 12. We can turn grams into moles. Look up the element's atomic mass on the periodic table. That's its number of grams per mole, and do the calculation. The last step is to take all those moles and make a formula out of them. And there is a little bit of finesse to that, and we'll show how to do that as we do this example. So the first example we're going to do is Freon. Freon is a refrigerant, or it used to be. It's now banned. Freon is capable of disintegrating ozone as a catalyst. What that means is if you get a little Freon in the atmosphere, it reacts endlessly with ozone. It doesn't use up the Freon. The Freon gets preserved. And so it just leads to wanton destruction of the ozone layer. And that's really bad. So the Clean Air Act, a long time ago, banned the use of Freon. And we have since repaired the ozone hole over time. It's gone more or less back to normal. So if you're worried that like environmental action can't happen without like crazy amounts of change, it can. We just have to put our minds to it. So yell at your government wherever you are. Like, do more for us. We care about the environment. So what we need to do for this problem is figure out the empirical formula for Freon 12. Now, I've given you a mass percentage. And you might think, well, how the heck am I supposed to know how much I have in mass, right? I could have any sample. And you're right. We could have any sample. So what we're going to do is we're going to make it really simple. If you're doing an empirical formula problem and you have a mass percentage, the first thing that you should assume is that you have a sample that is 100 grams. If I have 100 grams, then 9.933% of that would be carbon, or in other words, just that number. And I can do that for all of the elements because it's exactly 100 grams. Okay. So that was step 1. There you go. Easy as that. Step 2, we're going to turn everything into moles. So we'll just do this. I'm going to turn grams of carbon into moles of carbon. I'll look up the molar mass. 1 mole of carbon is 12.01 grams. And I'll figure out the number of moles of carbon in my sample. So for this specific sample, I got 0.827. I get one more digit. 1. Let's repeat that for chlorine. 1 mole of chlorine is 35.45 grams of chlorine. And we'll punch that in the calculator. I lost a decimal point, so my answer is Garbo. There we go. 1.654. I'm going to sneeze. Hold on. Sorry, that took a second. We'll do fluorine. Oops, if I can pull this down a little bit. One mole of fluorine is, I think it's 19? 19, yeah. 19 grams. We'll punch that in the calculator too. And what you'll notice is that, I got a very similar number here, didn't I? And that's by design. You'll always notice that when you're doing these formulas, is that the numbers will be similar or even have a ratio. You can probably tell the ratio by looking at it. This one is twice as much as the other ones, right? But let's assume that you couldn't tell that. We have all the moles, so we got to make this into a formula somehow. So here's what I'm going to do for my formula. So step 3 is to make a formula. I'm going to write this in another spot. And I'm just going to write what I have. C 0.8271, Cl 1.654, not O, fluorine 1.655. Now, that's not a formula, obviously. In fact, we're going to give it a name. This is a pseudo formula. It's kind of like a formula if you could have decimal numbers for elements. But it does resemble a formula, right? So now what we're going to do for our pseudo formula to turn it into an empirical formula is we're going to divide by the smallest number. In this case, ooh, excuse me, when I sneezed, like, everything came loose in my sinuses. That's disgusting. I'm sorry. I shouldn't have said that. We're going to divide by the smallest number. That's this number right here, 0.8271. And when we do that, we'll get the actual empirical formula. So the first one is C. C, 0.8271 divided by 0.8271 is just 1. CL, 1.654 divided by 0.8271 is 1.9997. That's real darn close to 2. We're going to round it to 2. And then for fluorine, same thing. 1.655 divided by 0.8271. I get 2.001. Again, real close to 2. There's your empirical formula. So what did we do to do this? Again, step 1, we wrote out all the masses. If I give you a percentage, you can just assume 100-gram sample. Step 2, we turned it all into moles. Again, very easy to do. Step 3, we constructed the pseudo formula and then divided by the smallest number that was present there to get the empirical formula. There you go. That's all there is to determining an empirical formula. So on these slides, oops, I kind of skipped over some of it. So again, first assume you have 100 grams. There's our samples. We turn those into moles. We then make the formula. This is actually a pseudo formula. We're going to divide by the smallest number, and we get this as our result. All right, you've seen me do it. Now I want you to do it. I'm going to give you whatever this is. I think this is Wellbutrin. It's like an antidepressant and also a stop smoking medication, but it's also used for other things too. So what I want you to do is, using this empirical formula elemental data, tell me the empirical formula using the same process that we just did. There's 5 of them, but you can do this relatively quickly once you get started. So write out all of your masses. Again, assume you have 100 grams. Turn it all into moles. And then write the pseudo formula and then the formula. And you should notice a lot of your numbers line up. All right. I'll check back in with you in about 5 or 6 minutes. We'll go over the answers at that point. 2 more minutes, we'll go over the answers. All right, let's go over the answer. Oh, I gotta capture all of these on here. All right, so we're gonna do the same process, but we're going to have 5 elements instead of 3 this time. So I'm gonna assume 100-gram sample, and we'll just do these one at a time here. So 1 mole of carbon, 12.01 grams, right off the periodic table for that. 0.15 over 12.01. I hit the wrong button. And I get 5.258 moles of carbon. We'll do that for hydrogen. One mole of hydrogen is 1.008 grams of hydrogen. I get 7.510 moles of hydrogen. We got 14.879 grams of chlorine. And then grams of chlorine per mole of chlorine. 1 mole is 35.45 grams. And I got 0.4172 moles of chlorine. I just realized up here I gotta erase one of these digits. I only get to have 3 sig figs. For nitrogen, I have 5.84 grams of nitrogen. One mole of nitrogen is 14.01 grams. Punch that in the calculator. 0.417. And then we'll scroll down a little bit and put O in there. And 1 mole of O is 16 grams of oxygen. And I get 4.1 or 0.417 for that one too. So obviously the last three are going to have the same coefficient. They're also the smallest number. So we'll write our formula here. I'll try and squeeze it in here. C 5.258, H 7.51, Cl 0.4172, N 0.417, O 0.417. I ran out of space. Oh well. We're going to divide by the smallest number. That looks like it's 0.417. And so these last three are just going to be 1. But C, 5.258 over 0.417 is... Did I make a mistake somewhere? I didn't get a whole number. And I really should have. Oh, I see my issue. I superimposed two numbers, so that's going to change this. .423. There we go. Okay, so if I divide that by 0.417, I should get, there we go, 13.00. So C13. For H, we'll do 7.51 divided by 0.417, and we get 18.01. And then the other ones are all 1. There's our empirical formula. Let me scroll that over a little bit. There you go. So a lot of work to solve that one. So I have one more for you to try on the next page here. Now for this one, I already gave you the masses. I didn't give you a mass percentage, so you could just use these masses. And I want you to tell me the empirical formula of ibuprofen. I'll give you 5 minutes to do that. We'll go over the answers and we'll take a break. And then we'll talk about the lab because you now know everything to do the lab. 2 more minutes, we'll go over the answer. All right, let's look at this. There we go. So we got 7.568 grams of carbon, 0.881 grams of hydrogen, 1.551 grams of oxygen. Let me make sure I wrote those down correctly this time. Yeah, that looks good. All right, so we turn it into moles. And this is 0.6301. All right. We're going to do the same thing for hydrogen here. 1 mole, oops, cancel these out. 1 mole of hydrogen is 1.008 grams of hydrogen. I get 0.874. And 1.551 grams of oxygen. One mole is 16 grams. I get 0.0969. Oh, 9694. So we'll make my pseudo formula down here. So C 0.6301, H 0.874, O 0.09694. We'll divide by the smallest number. That's oxygen's number. 0.6301. Divided by 0.09694. And I get something really interesting here. I got 6.500. That's weird. How the heck am I going to round that? Well, let's just leave it and we'll come back to it. So for H, I got 0.874 divided by 0.09694. Let's just not worry about it right now. I didn't type in a number. This calculator. Might be time to replace my old TI. I got H9.01, which we're just going to leave as 9. That one's close enough. And then O. So I have a fractional issue. I have C6.5H9O. Well, you can't have fractions for atoms. In the same way that if I tried to make the empirical formula of something like this, by dividing it by 2, I would end up with this. Right? So if I divide by 2, I would end up with fractions here, which is not allowed, right? So what has happened here is that by looking at the ratios, I've gotten the simplest ratio, where something is 1, and then the rest is whatever it is. So to undo that, I would just have to multiply by 2 to get rid of the fractions here. Now in our case, we just happen to divide and set one of them to 1, but then I got a fraction as a result. And since I can't have fractions, I need to multiply to get rid of this fraction. So I'm going to multiply everything by 2 to get C13, H18, O2, which is the correct empirical formula. Now, how do I know that I had to multiply by 2? Because I landed on a fraction. And really what that means is that if you end up with fractions, then your empirical formula doesn't have a 1 in it. You're going to get to some point where you can't divide out a number anymore. So here, if I try to divide by 2, I get C6.5, H9, and O1, which obviously we can't do that. We can't have a fraction. Okay, so sometimes that does come up. Look for fractions that you can multiply away, particularly if you land on like 0.5. You might also land on 0.333 or 0.25 or something like that. And just be mindful that those possibilities exist. Otherwise, you do it exactly the same way as we've already done. All right, let's go back to here real quick. We're going to skip that for now. We're going to take a break. When we come back from the break, what we're going to do is we're going to talk about the lab first, and then we'll do molecular formulas, because there's like 1 or 2 more slides, and then we're done with the unit. And we'll call it a night. We don't need to do Unit 14. We'll do that on Monday next week. All right, so I'll start the timer. I'll get the music going again. And I'll see you in 10 minutes. Alright, we are back. So let me scroll this down real quick. And then we'll go over well, we'll go over here actually. Alright, so let me put that oops, that's the wrong. That's the soundtrack I'm playing. There we go. I didn't click over on the screen enough. Okay, so I'm on Canvas now. You know, we really only need this part. This is lab number 4. So we'll scroll. Let me scroll all the way back to the top here. Okay, so the purpose of lab number 4 is for you to calculate experimentally the formula of an unknown hydrate. Now, what a hydrate is it is a compound that has an ionic compound, but it also has water attached to it. So hydrates are just like ionic compounds, but water is also incorporated into the lattice. So the way that we would write a hydrate would be along these lines. So we would write something like this. So if I had say a calcium chloride hydrate. So there's calcium chloride, and we put a dot, and then we put some number, H2O, for how many water molecules there are per calcium chloride. And this could be any number from 0 to 10 or even more. Sometimes they have more than 10. But it is going to be a whole number because there's going to be some number of waters in there. With one or two rare exceptions, you can get a half for water in this case, which means that there's 1 water per 2 formula units. None of our examples will have that, but we're looking for a number to put in there in that spot. Now, let me erase this, and we're going to just replace this with a generic ionic compound. X, Y, and I'm going to put Z for water. So let's suppose I have some copper chloride that is also a hydrate. And what we can do is we can find the number of moles of copper, find the number of moles of chlorine, and the number of moles of H2O. And if we did that, we would be able to make a pseudo formula out of them. So the number of moles of copper would be X, the number of moles of chlorine would be Y, and the number of moles of H2O would be Z, and you'd put them all in the spots that are assigned. Notice that the Z goes in front of the water and not a subscript after it. From there, you just treat it like an empirical formula problem. Divide by the smallest number, and that'll give you the ratio of copper to chlorine to water. And if you have any fractions, deal with them that way. You probably won't end up with any fractions. Now, in the experiment, we determine the masses of our substances experimentally. So, for instance, in this first example here, with this compound, here's my hydrate. And if I heat the hydrate, the water will come off of it. It will boil off. So we do this in a tool called a crucible. And here's my crucible. I've got the hydrate in here, and the little circles represent water, and the X is just the ionic compound. When you heat this, the water escapes. Now, how does it escape? This lid should be slightly open. But of course, like, it's hard to draw these pictures. I didn't draw this picture. I just copied it from somewhere. Never heat a closed system. If you're ever at home, do not heat something that is sealed. Make sure there's always a place for the gas to escape, or else you're going to make a bomb in your face when you're heating it, and that's no good. Once the water has evaporated, it's gone. But what we can do is, before you heat it, weigh the sample. After you heat it, weigh the sample. The difference would be the water that was lost. So, down here, I actually have a video of doing this experiment. And what they're going to do is they're going to show you, okay, here's how we figure out how much water is lost. They're going to show you the experiment. Here's how we figure out how much copper is in the sample. Here's how we figure out how much chlorine is in the sample. Oh, wait, sorry. They use a different hydrate here. They use copper and sulfate here. So what they do for their experiment is they figure out just how much water is in here in this sample. And then you're going to figure out its formula by filling in X. I've already told you the formula of the compound. We don't need to isolate the copper or the sulfur for this case, because I've already told you it's 1 copper per 1 sulfur. But how much water is there for that hydrate? You'll find out by watching the video and recording your information in this data table right here. So this is number 7 on here. Watch the video. The hydrate used is this XH2O. Record the numbers as they do the experiment, because they're going to show you a balance. You could pause the video and write in the numbers in the Google Sheet. Once you know the masses of everything, you can then figure out, okay, this is the mass of the anhydrous sample. That's the copper sulfate. This is the mass of the water. I can turn those both into moles. I can then figure out the pseudo formula and the formula. And this will walk you through that. I have a few other examples that you'll do in this experiment. So this one is FeCl3.xH2O. Again, I've already told you the formula. It's 1 to 3 for iron and chlorine. but what we don't know is X here. So using this data, we can say, okay, here's the empty crucible. Here's the hydrated sample. That's before I heated it. I could subtract those two to figure out how much stuff I put in there. Then I could heat the sample and say, okay, well, this is what it weighed after I heated it. So before heating and minus after heating must be the mass of water. And then I can use the data that's here to figure out the mass of the dry stuff, which is just FeCl3. Then you can turn all those into moles and figure out the formula. And this experiment really is just do this over and over and over and over again. So in the pre-lab questions here, I ask you some descriptions, like what is a hydrate? Read the documentation. You can figure that out. I've already told you what a hydrate is, really. Then number 5 is, okay, I have a 1 gram sample of sodium carbonate that is hydrated. After it's heated, the dry sodium carbonate has this mass, and this walks you through how to do it, just like we've described just now. And then finally, at the end, there's a bunch of analysis questions for just some other experiments that could be done. The last question, number 9, involves hydrating something. So I give you the mass of chlorine to start, and then we put water in. It becomes a hydrate, and its mass increases. And so you do this process basically backward from what you did before. And that's lab number 4. It's very straightforward once you've seen the empirical formula lecture, because it really just comes down to, okay, find the moles of stuff, make the pseudo formula, turn it into a formula. In fact, on this right here, we have already done all of this part for you in these examples. In 161, you will actually have to do the solve for X and Y part, but this has already been done for you. We want you to do this part. So your goal is to figure out what goes in that spot there for Z. All right. Let me know if you have any questions about that. I do want to go over the molecular formulas here real quick before we call it a day. There's only like 1 or 2 more examples, so let's just do these. So you've done all this work. You've calculated the empirical formula of something. I want to know if it's actually the molecular formula. In order to do this, I need to know the molecular mass of the compound in grams per mole, which means that I need to do an experiment to determine this before I decompose it into elements. Now, there are other ways to figure out the molar mass of something. In 161, we're going to talk about mass spectroscopy, which is I accelerate it through a magnetic field and it launches at a detector and it tells me how much it weighs based on how much it curves around a bend. But there are tools to do this. But what I can do is I can say, okay, if I give you the molecular mass and you know the empirical mass, you can make a ratio between them that has the multiplier in there. So whatever your empirical formula weighs, whatever you solved for, figure out its mass. Use the periodic table or LenTech. Whatever the molecular mass is, I will tell you. Divide those two and you will get the multiplier. Now, if I multiply the mass by the multiplier to get the molecular mass, I should be able to do the same thing for the formula. So, for instance, let's suppose that I have done an empirical formula problem, and this was my answer, CH. And then I weigh the compound in the mass spec, and I learn that it weighs 78.11 AMU, or 78.11 grams per mole. So if I compare the molecular formula mass and divide by the empirical mass, I'll get the multiplier. Well, the molecular mass is just this. And I can write grams per mole, it doesn't matter. What's the mass of CH? Well, carbon on the periodic table is 12.01, and H is 1.008. So those two things together are about 13.02. And then I can divide these by each other, and I should get a whole number. And I got 5.99999. So this is what I got. So if I multiplied this times 6 to get the mass, I should be able to do the same thing to the formula. So here's my empirical formula. Here's the molecular formula. So in other words, figuring out the molecular formula is basically just do what you have done already with empirical formulas and then add this one last step to the end. Figure out what your empirical formula is in AMU or grams per mole. Divide the molecular mass by the empirical mass to get the multiplier, and then multiply your formula by the multiplier. All right, so let's do an example. So the first step here, I want you to determine the empirical formula of butane-dione with these masses. Hey, it's the same thing you've been doing all day. We'll do it one more time. So figure out the empirical formula. And once you've done that, here's the actual molecular mass. It weighs 86.09 AMU. Are the empirical formula and the molecular formula the same? Well, if they are, your empirical formula should have the same mass. If they're not, they'll be off by some multiplier. In that case, multiply your formula by the multiplier. So I'll give you 5 minutes to do this. Maybe a little longer, actually, 5 or 6 minutes. We'll go over the answer together, and then that's it. That's all we're doing for this section. Just as a heads up, this next section, we don't do it. I'm not going to do combustion analysis. You're not going to be tested on it. If you see it in 162, you can do it then. That's fine. All right, we'll see you in a bit. 2 more minutes and we'll go over the answers. All right, so let's go over the answer here. So clean out this. All right, so here's our masses. Something, something, we've done it all day. So we'll convert to moles. And I got 2.323 moles of carbon. Do the same thing for hydrogen. And 512 over 1.008. 3.484 moles of hydrogen. And then oxygen, 18.59. One mole is 16 grams. 18.59 divided by 16 is 1.162 moles of oxygen. So we'll take all this, we'll make our formula out of it. C 2.323, H 3.484, O 1.162. We'll divide by the smallest number, that was oxygen's number. And when I do that, I get C2 I swear this calculator is just trying to screw with me today. H3O. So there's the empirical formula. Now if I go over to Lentech and I type this formula mass into Lentech, which would be this window here, C2H3O, and it spits out the mass. This has a mass of 43.04 grams per mole. So let's write that down. Okay, cool. We got that part. But according to the problem statement, what I actually put into the detector has a mass of 86.09. So the molecular mass divided by the empirical mass will give me the multiplier, because they're not the same. So we'll just punch that into the calculator. So 86.09 grams per mole. Same as AMU. I just happen to write grams per mole here, so I'll leave it in that. And when I do that, 86.09 divided by 43.04, I get 2. So this is my multiplier. So I need to take my formula, and I need to multiply it by 2. So the molecular formula would be C, 2 times 2 is 4, H, 3 times 2 is 6, O, 1 times 2 is 2. And there is the molecular formula. All right. There you go. That's Unit 13. Any questions, let me know. You should now be set up to do both the questions in Unit 13 as well as the lab. Now, the next quiz is going to be Units 13 and 14. So we're going to finish 14 next week. So that quiz will be due week 10. And then the final quiz is Units 15 through 16, which will go up also during week 10, but be due after exam number 2. Quiz number 8 is the last graded quiz. Quiz number 9 is just a practice quiz. It's worth 1 point. You click a box and you get a point for it. And then you do all the other problems, and I just release the answers immediately. So that's what's coming up on the agenda for the remaining weeks in this class, because we're almost done. There's only 2 more weeks of class. Believe it or not. I'm grateful. I'm ready for vacation. I want to thank everyone for coming out to the lecture. We're going to stop here. We'll resume next time on Tuesday, actually, with the next lecture. So next week, Memorial Day is on Monday. Enjoy your holiday. Lectures next week will be both Tuesday and Wednesday because of the Monday holiday. So there will be another Monday or another Wednesday lecture next week. So we still get 2 of them. Check the syllabus for more details on the schedule. Other than that, there's really not much else to say. Let me know if you have any questions about the lab or the quizzes or the content. Hit me up in the Discord or send me an email. Have a great one. We'll see you next week.